Good morning, guys. You've been doing great with our online learning, and I'm just really proud of how you guys have been responsible in submitting your assessments. I think some of you might need to be a bit more careful about how you're taking notes because on the second day's uh, assessment, yesterday's, it seemed like there were some careless mistakes. So remember, you can always go back and watch those videos a second time, or even try to take your assessments while you're taking the videos. That's totally fine. And try not to make those careless mistakes. I think we can avoid some of that just with a little bit more careful listening. So today, I want to start off with a little thought experiment. And I want you to get a piece of paper out in front of you and imagine this scenario. Imagine there is a pitch dark room, and inside this room, there's nothing except a little table in the middle, and there's a vial sitting on the table, and this vial has some type of attractant in it, and this attractant attracts fireflies. Okay, so you've got your room, and in the middle of the room, right, of course it's pitch black, so you wouldn't be able to see it, but maybe you've got a little table in this room, and on the table in the middle, you've got a little vial with some firefly attractant, okay, and it's giving off some odors or something that attracts fireflies. Okay, so you've got a firefly in the room somewhere, and it's pitch black. Now, you know what fireflies do, right? They kind of light up every now and then, and you know, if you're outside and you see it light up and you go after it, and then it lights up somewhere else because it's moved away. And sometimes they're hard to catch because you can't quite see where they are unless they're lit up. Okay, so what I want you to do is imagine you've got this scenario with this firefly and this attractant in this pitch dark room. What would a time-lapse photograph look like if you observe this room for something like an hour or 2 hours or 10 hours? Okay. If you're not sure what I mean by a time-lapse photograph, I've got a few of these here that I've pulled up on Google. So basically you keep the lens of your camera open and it absorbs light over a long period of time. So instead of just an instant of time, you're getting a whole lot of light coming in. I love it with this street scene because you can kind of see the movement and that type of thing. And you may not know this, maybe you do, but if you have a time-lapse photograph of the sky, you get these really cool circular patterns because, you know, of course, our Earth is rotating, and it looks like the stars in the sky are moving in circles, but they're not really moving. It's the Earth that's spinning, and so we look up there and we see this. And so you know, if you're a flat earther person, you'd have a lot more difficulty explaining why stars move this way and they're all moving this way together. It's a lot simpler to believe that it's the Earth that's spinning and it looks like the stars are moving. But I love this perspective. And can you guess what star might be right here in the middle? Well, that's the North Star. It's the star in the sky that doesn't look like it's moving at all relative to the Earth. And so I think it actually moves a tiny, tiny, tiny bit. And scientists say that a few million years from now, the North Star will eventually not be our North Star anymore. But for the moment, it's sort of caught right up here, straight above the North Pole. And so the North Pole is somewhere up here on Earth, but everywhere else, you know, the Earth is kind of spinning, and it makes it look like the stars are moving in circles above us. Okay, but back to our scenario with the firefly. I want you to imagine that we've got a firefly in this room, and we're going to do a time-lapse photograph. What would that photograph look like after several hours? So take a moment, pause this video, try to imagine what it might look like, and draw a picture. And I'd like for you to spend 2 or 3 minutes doing that on your own before you continue the video. Okay, so what you may have come up with, if you're thinking about how the firefly is going to move, this is the way I would think about it. And there's not really a right answer, but there's probably some better answers than others. Your time-lapse photograph is not going to just look like this, because the firefly is not lit up all of the time. It's flashing every now and then, so it's not going to look something like that. It's not what the photo would look like. Even though the firefly might be moving that way, the photo wouldn't look that way. So imagine if the firefly is moving and then it lights up right here, that would make a little dot in the photograph. And if it flies over here, make a little dot in the photograph as well. And if it gets near this attractant, it's probably going to be spending a bit more time near the attractant, right? Makes sense. But then again, fireflies aren't super intelligent, might forget what it's doing, and then fly off over here and just sit on the floor for no reason. Okay, but then again, after a few minutes, decides to fly again, starts lighting up, and then it smells that attractant again. So it's going to spend some more time here near the attractant. So we can imagine this type of thing happening over and over and over again over several hours. And what we'll find is that the firefly will very likely spend a lot of time near the attractant and less time further away from the attractant. Okay, and so after several hours or something like that, you know, there's always a little chance it might be really far away in some corner of the room, but you know, I think it's very likely you would end up with a time-lapse photograph that looks something like this. Okay, it's going to be spending more time near that vial of attractant than anywhere else. Okay, so now why in the world are we talking about fireflies? Because it turns out electrons are kind of like this in the atom. You know, Niels Bohr thought that the electron orbited around the nucleus, but we're going to learn today that orbits are not what the electron in the hydrogen atom is doing, and it's something a bit more like what this firefly would probably be doing. Okay, so I want you to turn in your wave mechanical model packet to this page here, and we're going to fill in some blanks for today's lesson. And I think I'd like to get up through this page at least today. Okay, so let's get into it. All right, so the wave mechanical model of the atom. So Niels Bohr's model of the atom viewed the electron in the hydrogen atom as a particle that moved along fixed, allowed orbits. Okay, and remember that whole idea about the nucleus and then the electron being in an orbit here or an orbit here, these distinct allowed orbits, and it might get energized and jump up to a higher energy orbit, and then once it falls back down, it releases that photon. That was his model of the atom. And you get these distinct orbits at very specific spots. But the thing is, a particle, the way that Niels Bohr was imagining it, is very predictable. And an orbit itself, an orbit is very predictable. For instance, astronomers know exactly the day and time of the next solar eclipse. Which is pretty cool. But that's because we know the positions and the velocities That's a word for speed, of the Earth, the Sun, and the Moon. Okay, so we know the next time that, here's the Sun. We know the next time that the Moon is going to be in front of the Earth and it's going to cast a shadow, onto the Earth somewhere, right? We know when that's going to happen. That would be like a solar eclipse when the Moon moves in front of the Earth. So we can predict that type of thing. But the thing about electrons is they are not easy to pin down. In fact, the better you know an electron's position, the worse you can determine its velocity, and vice versa. This is something I mentioned when we first started this unit, and it's one of those mysterious things about these tiny particles is we're actually very, very limited in how well we can measure both of these things at the same time. With planets, there's not this trade-off. If you know where the moon is, it's not like suddenly you don't know how it's moving. We can measure both of those. We know that the Earth is orbiting, and we know that the moon is also sort of orbiting around the Earth, and so we can figure out when these things are going to coincide. There's not a trade-off in our knowledge of the position and the velocity of these things. But with the electrons, there is a trade-off. The better you know one, the worse you know the other, which is pretty weird. Okay. And this trade-off is something that you may have heard of before, maybe not, but it's called Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Okay. And that's named after the Austrian scientist, I believe, Werner Heisenberg. Okay, so electrons are more like the firefly from our thought experiment a few moments ago. And electrons also act a bit like waves. Okay, they seem to be all over the place at once. And it's hard to imagine anything like this. The subatomic world is very different than our own. It really is hard to visualize what these little electrons are like. And in fact, it's really impossible to visualize what they're like. It doesn't make sense to even talk about seeing something this small. That's hard for us to imagine. Okay, so again, there were a number of physicists and other scientists working on this kind of dilemma, figuring out what electrons were doing. But two ones that we need to know about are Werner Heisenberg and that's from the same guy from Heisenberg's uncertainty principle, and Erwin Schrödinger. Oops, there's a little special accent mark over the O in his name, Schrödinger. Okay, Austrian, and I think they may have both been Austrian, but I think Schrödinger might have been German. I don't remember. And these guys developed the mathematics to better describe the atom. So, it's sort of funny. Eventually, physicists realized that you can't really visualize this stuff. What in the world is a wave that acts like a particle, or a particle that acts like a wave? We can't visualize this stuff. But what's interesting is these guys develop some mathematics that perfectly model it. perfectly modeled the electron and in particular its behavior. Okay, so you know, mathematics, there's like some complicated mathematics that help us understand what the electron's doing, and but it's really hard to visualize. Okay, so the fact that the electron acts like a wave, we're going to focus our attention on, and that played a big role in this mathematics. We don't need to do the mathematics, but we need to know a little bit more about waves. Okay, so I want you to imagine you're holding a jump rope, 2 people holding the end of a jump rope, and you start swinging the jump rope sort of up and down and making it kind of bob up and down. So we can kind of draw this and kind of connect the 2 ends of the rope. That was terrible. Let me try that again. Come on. Boom. There we go. And we can imagine this kind of bobbing up and down, right? So that dotted line represents where it might be, you know, a moment in the future. Okay. And this is something known as a standing wave. Standing waves can occur on jump ropes. They can also occur in other contexts. The other day, I started up my car and there was a cup of water in the cup holder, and I was looking down and I saw these ripples moving through the cup, but the ripples weren't really, you know, propagating outward. They were just kind of stuck in place in a weird way. And that was a standing wave that was happening in my cup with the water. And so it's like ripples that weren't really moving through space. They were just kind of stuck in place. If you're careful with a jump rope, if this person over here kind of moves the rope upward and this person over here moves the rope downward at the same moment, you can get another type of standing wave to develop. And it's kind of fun if you kind of mess around with this a little bit. I'll show you a video in just a moment, but you can actually get a spot in the middle of the rope where there's no movement at all. And so you get a wave kind of moving upward on that side and a wave moving downward on that side, and they kind of alternate, like this one goes down while the other one goes up. And this little spot right there is called a node, where there's no movement. And you can actually get more complicated standing waves where you get like 2 nodes, maybe like here and here, and you get an upward movement here and a downward movement here and an upward movement there. A little bit harder to draw with this tablet. But all of these things are various types of standing waves. And you get these little nodes where there's no movement in the wave at all. And standing waves are kind of like what the electron behaves like. So electrons do this very thing. How in the world can a particle do that? We don't really know how to visualize that. Note that if you want to speed up the wave, the standing wave, in a stable manner, you can't just do it any old way at all. Only certain wavelengths would be allowed on that jump rope. And there's that word allowed again. Remember that different energies were allowed inside the atom? And not every energy, but you have these distinct energy levels, right? Like, why in the world should there be these distinct energy levels? Niels Bohr, he really wasn't quite sure, but it seems pretty clear why for a jump rope. If you start wiggling a rope any old way, you might not be able to generate these nodes, okay? And so this is a clue that electrons in the atom have wave-like properties, okay? And the electron and the hydrogen atoms behave very similarly. And since the electron seems to be a particle, we will represent its location in an atom as a probability distribution. Probability distribution. Which shows where the electron is likely to be found. A probability distribution is also called a probability map, and we'll see these in just a moment, but there's going to be something very, very wave-like about these probability distributions. Okay, so this is how we can kind of bring together the particle idea and the wave idea all together. And so we'll get to this page in just a moment, but I want to show you a video about standing waves. This video is posted on your portal page. Okay, so if you navigate to your portal page, let's see. Right. And if we go here, topic folder, down here, standing waves on a rope. Let's go ahead and watch this video together.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode.
So what we are seeing there is a standing wave. He starts moving it up more quickly. That's another standing wave with a node in the middle. And you can see it's not really moving there in the middle. And if you go a little bit faster, you get two nodes. Okay, so those are standing waves along a rope. You can also get other standing waves that are like two-dimensional. And so this is a good video to watch, but you can watch it on your own. We're going to watch it without the volume turned up here. Learn about Grammarly for a moment. Get out of here. Okay. By the way, this girl in this video is extremely energetic. She's kind of crazy. But if you jump forward, basically she starts off with a device that you can kind of crank up some vibrations on, and she pours some sand on a plate, and let's go ahead and watch.
Why does this happen? As I tune the plate to vibrate at very specific frequencies, or notes, the sand moves on the plate into beautiful, though unusual patterns. As I find higher and higher special frequencies, the patterns on the plate get more intricate.
Okay, so basically we're getting interesting patterns just from jostling sand particles around on a plate. And I think she talks about like how there are little spots on the plate, let me see here, where you get nodes. So here where the sand ends up collecting, that's where the plate actually isn't vibrating at all. And here where there's no sand, it's because the plate is bobbing up and down so much it throws the sand particles away, and they sort of find their spots in these nodes. Okay, and so she's cranking up the frequency, and we get these very specific frequencies.
Oh, unusual patterns. As I find higher and higher special frequencies.
Okay, so again, a bit more difficult to understand how this is happening, but I encourage you to go back and watch this video. You can get standing waves on a rope, you can get standing waves on a plate, and apparently in the atom we have something like standing waves with electrons. Okay, so we're going to learn about these standing waves today, and then hopefully finish up today's lesson. Okay, so standing waves for electrons. Okay, so Niels Bohr was onto something, correct? Okay, that we have these distinct energy levels, and he thought that they were orbits, but it can't be an orbit because an orbit is very predictable. Okay, and electrons are not predictable. They're like fireflies, so how can we put those two ideas together? Well, in this wave mechanical model that Werner Heisenberg and Erwin Schrödinger come up with, we enter into the modern understanding of what the atom is like. Okay, so what are we going to replace the orbit with? This is something called an orbital, and an orbital only shows us where an electron is likely to be found. It's like a firefly. You're not really sure where it's going to be at any given moment, but you can be confident where it's likely to be. It's not the same thing as an orbit, right? You know, in our thought experiment, the firefly was not, there's no way that a firefly would be doing something like this, right? Just over and over and over and over and over again. It's not how fireflies behave, you know? And if I asked you right now, where is the firefly? You couldn't really tell me. You know, it might be here, right? It might be here for some strange reason. But if I asked you, where is it likely? You could be pretty confident, right? You could be pretty confident that it's likely somewhere in there, right? Somewhere in there. And so it turns out the electron, we don't know where it's going to be at any given moment, but we can be very, very confident about where it's likely to be. And so we're going to draw something very, very similar right here in the packet for the electron. And so this is something called the 1s orbital, and it represents the ground state of the hydrogen atom. And it looks a lot like that firefly thought experiment. So if the nucleus of the atom is right here at the origin, and by the way, this is a set of three-dimensional axes. If you've never seen this in math before, you've got your XY plane, but you also have a Z-axis, which is going into the picture and then behind the picture. So this is three-dimensional, okay? You know, for instance, like a cube is something that's three-dimensional, right? You guys have seen that before, right? Cube's three-dimensional. This is three-dimensional here. And so the electron is very likely to be near the nucleus. So I'm going to put a bunch of dots here. But as we move further away, it becomes less and less likely that we find the electron. And this is called an orbital. It's a probability distribution of where we might find the electron. So in your packet, go ahead and make a bunch of dots, kind of like what I'm doing. Again, it's possible you might find the electron out here, but the further we get away from the nucleus, the less likely that becomes. And so eventually, you have the entire probability map. The closer you get, the more and more likely it is. And it looks kind of spherical. This is a sphere. Okay, and it is possible you could find the electron out here and here and here sometimes. It's true, right? You just don't really know for sure, but you can be confident about where it's likely going to be. Okay, so this is something called the 1s orbital. And that's very different. It's very different than the way that Niels Bohr thought about the movement of the electron. But this is the current understanding of how the electron behaves. Some people call this thing an electron cloud, right? And so, you know, because clouds are kind of fuzzy, right? But I don't really like that idea because clouds are made up of lots and lots and lots and lots of particles, and you can see a cloud very, very clearly. This is supposed to represent the probability of finding where one single particle is at a given instant in time. Okay, so it's a probability map. Okay, the name of this orbital is called the 1s orbital, and there's two parts to the name. You have this number and this letter. The number indicates the energy or size of the orbital, while the letter, in this case S, tells us the shape. So tomorrow we're going to learn about different orbitals that exist in the hydrogen atom. You know, just like there are these different shapes of standing waves that we can get on this plate, there are different shapes of orbitals for the electron in the atom. But they start off pretty simple. Like that first standing wave was pretty simple looking, and it even had this little circle around the middle. As we get more and more complicated, she's crazy. As we get more and more complicated, the shapes get a bit crazier. Okay, and that happens with the hydrogen atom as well. Let's see if we can finish this up today. View page width, and let's zoom back in. Okay. Now, Niels Bohr thought that there were lots and lots of orbits at distinct spots in the atom, these excited states of the atom. What are we going to do with those? Well, there's different standing waves, different orbitals. There are other ways to excite the electron. And in the atom, just like we can, excite a rope and get different types of standing waves with different numbers of nodes and things like that on a rope. And just like on the rope, only certain higher energy orbitals are allowed. Okay, and we're going to see a little bit today, but more tomorrow, that the size the sizes and numbers of orbitals, and they have different shapes. We'll see. The number and the sizes of these orbitals increase the further we move from the nucleus. Okay, so here's our ground state orbital, the 1s orbital. So what about the first excited state? Okay, all of the orbitals on this next page occur in the second energy level. These 4 orbitals occur in the second energy level. And for that reason, they're all going to start with 2. And we'll fill in the rest of the name in just a moment, but they're all in the second energy level, so they're all going to have a 2 there. Okay, so in the first energy level, we saw the 1s orbital. In the second energy level, there is a 2s orbital. And the 2s orbital, it's like the 1s, it's just bigger. Okay? And so, this one, if you're going to draw a boundary around it, and scientists actually do this, they try to draw a boundary around 90% of the probability. Maybe that's 90%. That's a 90% boundary. Once you draw a boundary around it like that, to enclose 90% of the probability, you can see the shape of this thing. Okay, and so the electron would spend 90% of its time inside that shape right there. It's a spherical shape. But again, it's kind of fuzzy because these aren't solid things. This is just showing us where an electron's likely to be found. So here on this next page, the 2s orbital, it has the same shape. It's an s orbital, so it's spherical. Oop. It's just going to be bigger. So let me see if I can do this. Come on. Still learning to use this tablet, so thank you for your patience. So it's just a bigger sphere this time. And I'm not going to draw it three-dimensional, there's no need, but just keep in mind that it is three-dimensional. Okay, and so there's my 90% boundary again. It's just a bigger boundary. Okay, and if you want to, you can go ahead and put some dots here in the middle. 90% of the time, if the electron is in the 2s orbital, 90% of the time it will be in this region of space. But then again, 10% of the time it could be anywhere else outside. You just never know with the electron. It's impossible to pin down. It's not like an orbit. Okay, so I could spend a lot of time trying to make that look nice, but from this point on, we're mainly just going to draw the boundaries, the 90% boundaries, because those are easier to do than a bunch of dots. So in the second energy level, there are 3 other orbitals. These are called the p orbitals. 2p, 2p, 2p. And a p orbital, what's it look like? This actually has a node on it. Remember our standing waves on the rope? That one in blue didn't really have any nodes. But then this one in green had a node in the middle. And then there were more and more nodes the more complicated these standing waves got. And so these three-dimensional standing wave orbital things, they also have nodes. And so they look a bit like this. It's called dumbbell shaped, where you have, again, it's three-dimensional. Try that one more time. It's really difficult to draw with this tablet. I'm still learning. Let's scoot that up. Boom. Okay, so they're kind of, ideally I would have drawn those the same size, and it's, in terms of its width, it's about the same width as the 2s orbital because it is in the second energy level. This one's called the 2px orbital because I've drawn the orbital on the x-axis. I've drawn it along the x-axis. So that's 2px, and there is a 2py and a 2pz. The 2py orbital looks exactly the same, but it's situated on the y-axis, so it's pointing upward. And like that. And then the z-axis is coming out toward us in a way through the board, through the screen. So a little bit harder to draw to scale, something like that. It's on the z-axis. Now again, if you wanted to, you could draw a bunch of dots, but what we have here in red is the 90% boundary. Okay, 90% boundaries, okay, for all of these. All right, so in the second energy level, we have a 2s orbital and 3 p orbitals. And these are said to have a dumbbell shape. P orbitals are dumbbell shaped. If you guys lift weights, a dumbbell is that type of weight that you can hold in one hand and it has weights on either side. Seems like a strange name, but if you remember some of like the old school weights, if you've seen pictures of people that lifted weights like back in the 1920s, like old school weight lifting dumbbells. And at any rate, if you kind of look around for some of those types of things, don't quite see any of them, but these are more like modern dumbbells. But there's like, this is the type of thing, you know, like in like the 20s, or, you know, have these kind of big weights on either side. And so I guess some people thought that these things look like dumbbells and they called them dumbbell shaped. Okay, but that's sort of the official name for them. So you have these spherical shaped s orbitals, the 1s orbital, and then the 2s orbital, which is just bigger. They're spherical shaped. And then p orbitals are dumbbell shaped. Now tomorrow we're going to learn that there are lots and lots of other orbitals. And, you know, we're going to learn that the further we get away from the nucleus, like if this is the nucleus down here, the further we get away from the nucleus, we get more and more and more orbitals, and we'll talk about those tomorrow, and we'll learn how their energies relate to one another. Okay, so for the time being, let's just call it a day.